Yeah, well, yes. So today I wanted to talk about depth-first search. So that is the second of most useful and most used and popular traversals on graphs, as well as depth-first search. So this another fundamental traversal and search algorithm on graphs. It is used to explore and traverse nodes and edges on the graph. So its time complexity is the same as the time complexity of depth-first search, that is O of V plus E. So I think that is the best time complexity for traversal algorithm, because we have to traverse each edge and each node, and that is why the time complexity here is V plus E. So it is a it is usually it is most often used as a building block in building different algorithms and yeah, other methods on graphs and graph theory. So it is particularly useful for one thing, that is finding the shortest path on unweighted graphs. However, depth-first search is also useful for finding the shortest path on unweighted graph. It might be a bit more less obvious how to build depth-first search on to find the shortest path on unweighted graph. However, even if in this case that it is a bit less obvious, it is also pretty useful depth-first search. And today on Moscow Olympiads of students, I have implemented this depth-first search on one particular problem on finding the shortest path. So they are both useful. They are both are used, but breadth-first search a bit more often on to find the shortest path. However, it is a bit more complex to implement. All right. So yeah, let's look at how this algorithm works. So a let's look how this breadth-first search works. So as its name suggests, the breadth-first search starts breadth first. So it starts on some arbitrary node, or if we want to find the shortest path on starting node, so we're starting on a node, and we're exploring first every each neighbor node before moving to next level of its neighbors. So alright, let's start for example from node 0, and at each iteration we're going to traverse to every neighbor node. So first within depth first search we would go first go to 7, then to 3, and continue to traverse depth first. But here we're going to traverse breadth into each node, so 9, 7, and 11. So within then we're continue to traverse through its neighbors. There's a 10, 8, 3, and 6, and so on. So that is how the algorithm works. But however, the computer cannot traverse through a lot of nodes at once, because the computers we're currently using are not quantum, so they cannot make multiple operations within one operation. Yeah, so let's look how it works. So instead of implementing the quantum computing, we want to implement a queue data structure, and let's look at how it would work. It would work for us, how it would help us. Alright, so we're starting with 0, and next we're traversing through each neighbor of this node. As the same as with depth first search, so we're starting a for cycle for each node, but we're not traversing in depth. However, we are remembering each node we're going to, so that's 9, 7, and 11. And next step, what we're doing is that we're popping 0 from this queue as we have visited all its neighbors, as we have traversed and added to the queue all of its neighbors. And at this point, we are, one moment, yeah, one more, yeah. So at this point, as we've passed through, we've looked through 0 and all its neighbors, we have to go further. and we're going to go. Well, we're going to go to the next element here in the queue, that is 9. So we're traversing all of its neighbors of 9, that is 10 and 8, and as we've passed through all of its neighbors of that these are 10 and 8, we're popping it from our queue and going to next, that is 7. So we're not going to from 10 we're going to 1 and so on. So we're not going in depth, we're not going from the end of our queue but from the beginning each time. So we can call this as some kind of DFS, as some kind of breadth first search on a stack, but that is not right, but that is how it works. So the breadth first search traverses from the beginning of the queue and depth first search from the end of the queue. So it traverses depth in every time. All right. So let's look at how it works. So from 7 we can go to 3, to 11, 3, and 6. So normally we wouldn't go to 11 since we do not want to create a cycle here, because when we're traversing through a graph, we typically do not want to create these cycles, in order, if we don't want to break some of the algorithms we're working on, because breadth first search is usually a building block. So yeah, we would normally do not want to do this. However, next we'll go to 11, and since there 11 has no neighbors, we're going to next node in the queue, that is 10, and 10 has only one neighbor, that is 1, which we're adding to the queue, and we're traversing next. We're popping 10 out of the queue and going to 8, and the neighbors of 8 is 12, so we're going to which, so also 1, so we're creating a node to, we're creating an edge. If we want to direct this graph, we're making an edge to 1. Yeah, and also here we're making DFS to direct each node. If we do not want to direct it, if we just want to create some kind of a tree, that means that we do not want to traverse 1 here, but if we want to direct each node, then yeah, we're going to 1. All right. Next, we're traversing each node of each. We're continuing traversing through a queue. That is, we're going to 6, and the neighbor of 6 is 5. Where each we're adding to the queue. Next 3, we're going to 2, 4, and now each node is traversed, and we have just to go through queue. Yeah. So that is how our algorithm, breadth first algorithm, works. So, however, it is a bit more complex than depth first search, because in the implementation of depth first search, we just have to go in depth each iteration. But here, we need to keep the queue, and let's talk about it a bit further. So here, we're using a queue. So, yeah, the queue, we can call it as this data structure is that we are using to track which node we want to visit next. So we're adding to the end of the queue, to the back of the queue. We're enqueuing some element. We're recurring an element, and we're dequeuing from the front of the queue. So that is just like in the real world situation, real world queue, that people are enqueuing, they're entering the waiting line or getting seated if at the restaurant or on the boarding to the plane, etc. So these data structures works as follows. Yeah, and now let's look at code implementation of this algorithm, breadth first search. So it is a bit more complex than a depth first search. However, it is on some application it is more useful than breadth first search. And also another exception that this is not the only implementation of depth breadth first search, because we can implement it without all of these BFS, without these three functions. We can do it with only one. However, this is for code readability, so the code is much more readable if we do solve function. If we do reconstruct path, we can of course we can mix it up, we can combine it, and the code would be very ambiguous, but, or how is this word? Yeah, but in this case, the code is pretty yeah, comfortable to read. All right, so let's start with the block of defining variables. So that is the number of nodes in the graph and the adjacency list that is representing our graph. So we're starting with also declaring the function. So the BFS function. So here, this BFS is, by the way, just the yeah, so here, this is just for the convenience and usability of working with this. So the user, the programmer in the main block of the code just calls the BFS of starting node and ending node, and it works everything inside. So the programmer do not have to handle with solve function inside it and reconstructing path inside it also. Yeah, so that is just the constructor, we can call it in this way. So we're starting our BFS, so prev, that is the list of how this word, that is just the массив предков. One moment. The vector of ancestors. The translator says ancestors.
Yes. Ancestors. Yeah.
Yeah, ancestors.
Okay.
All right. So
Okay.
yeah. So we're now inside the solve function. So
okay.
Within this function, the algorithms works as follows. So of course, first we are creating the queue, which is the main. We can call this the main block of this algorithm. This data structure is what makes this algorithm possible. So we're enqueuing the S, that is the starting node, and next we're also declaring some more variable, some more data structure, yeah, some more lists, arrays, whatever. So the first is visited. These are, or we can also call it used, whatever. Sometimes it is also called color because not to rename used before variable names, whatever. And next, that is the prev, that is the list of ancestors. So next, we're traversing while the queue is not empty. So when the queue is empty, that means that there is no more nodes we can traverse in our list, and we would stop our traversal, stop our search algorithm. All right. So next, we're declaring a node. We're not declaring, we're just saving the value of the last value in the queue while deleting it. So we're dequeuing an element and saving its value and the node variable, and next, that is the neighbors. And this, what it does is just getting all of its neighbors. So by the way, that is just the G of node. So we're just getting all of its neighbors. In this case, in the adjacency list, what we're using, it is very efficient to do this. So next, we're going to the for loop, that is on all of its neighbors. We can just call for of next of G of node, but that is all, yeah, just for readability, because the pseudocode must be readable to build it on every other programming language. Yeah. So next, if we're traversing the node, if we have not visited it before, in this case, we can make more conditions. For example, if, yeah, on the statement of the task of the problem, we can write additional conditions here, and also what the algorithm, however, does is just we're enqueuing the element, each of the neighbor of node we're now traversing. We're queuing all its neighbors, and making their values of the visited array of them to be true. So we're just marking them as visited and adding value to the prev array. And yeah, that is how our algorithm works. Yeah, so the main block here is just these three strings of code. So just we're adding the element, and by the way, yeah, we're just adding the node to the queue, and then we're traversing all the neighbors in this queue. So the queue here is the main element. All right, back in our BFS function, let's look at how reconstruct path works, because we very often we must have the ability to reconstruct the path from S to E. Yeah, that was the problem on the Moscow Olympiad of students. The task was to find the minimum path from starting node to ending node, and the problem was here, the main difficulty was to import the data, because it was given in a very strange format of, however, this task is not very easy, not very complex. It is a bit, it's just right, it is, it is quite straightforward. All right, so in the reconstruct path, what we're doing is that we are traversing through the prev array. We're just going through the prev array in the case that we're declaring path variable. So the path variable, we can call it ans variable, res variable, whatever. That is just the result of the reconstruction of the path. And next, what we're doing inside this for loop is that we're traversing through this prev. So the first node, the first value we're traversing is at ending, and from end we have to know from which node we came to end, and that is this part prev of the index we're looking at is equal the variable we're looking at, the pointer in the prev array we're looking at would be equal to the value of prev array at this point. Yeah, so here we're just backtracking. We're just we can call it this backtracking through through these prev array. So this, however, this is a pseudocode. It must be readable, but however, this block is not pretty obvious. So the normal code must, one moment. And it works. However, that is not from the today's Olympiad because its results are not yet known. Not each published. Okay. So we cannot look at our solutions that we've made.
Okay.
However, I can find at which from the contest system from Code Forces that we've made on the program and series. Yeah, so here it is, the problem on code forces to find the minimum path in unweighted graph. So these are some wrong solutions, and the solution that works here looks like that. So the BFS works like this on practic. So yeah, this code is also quite unreadable because we've wrote it on, how to say, na skorost писали его.
Quickly.
Yeah, quickly.
Or hurry.
Yeah, we wrote it ASAP. Yeah, we hurried. Yeah, so this is we're saving the value from the queue, and next we are these are the same 3 strings as in the pseudocode. So we're checking if the distance that is currently if it is greater than the distance from.
We would say these are the 3 lines, not 3
lines.
strings of pseudocode. Lines of pseudocode.
Thank you.
Yeah, no
3
problem.
lines of pseudocode. Yeah, and the reconstruction works just like this. We're traversing while the current is not equal to starting node. So we're starting with finishing node, and while it is not equal to starting node, we're just now processing. We're adding its value to the answer vector.
I think you want. Okay, I'll write it down.
Sorry.
I think we just say final node, not finishing node.
All right.
But that's
final
okay.
node.
I'll write it. Yeah, no, that's
all right.
Yeah, it's
so
not a big deal.
While it is not equal to starting node, we're adding its value to answer, and then we're backtracking one node and this array of the ancestors, and next, as just like in the pseudocode, we're reversing. We're reversing this because we've started from final node to starting node, and we want to start from starting and finish from finishing. This is why we're reversing it, and we are printing the value. We're returning out the value. This code. This is the input part. This is the BFS part. Yeah, so this code works on each test. Yeah, so this solution works. Here it is. These are the same parts. So we're making the reconstruction of the path, or we've called on the educational program, we call this the recovering of the path. And next, what we are doing is reversing the path and printing the path if it is. However, if as an ER connected, we are returning the empty list. Otherwise, we're returning the path. That is the answer, the same thing. Yeah, so I think that is the end of today's talk. I'll wrap up here. Thank you, Robert.
Oh yeah, no problem. Yeah.